Hey folks, this is the Unit 4 Day 4B lesson. So this is something that's optional for the regular MCV4U, but if you are planning on taking the AP Calculus course or exam, this is something there's a few special limits that will appear that you need to be able to evaluate for that exam. So this covers those topics, and it's the limits of trig functions. So to start off, some trig functions can just be evaluated directly. So for example, if we have the first ones here, the limit as theta approaches 2 pi over 3 of sine 3 theta over 3 theta. There's nothing bad that's going to happen. You can always just try substituting, and if you don't get an indeterminate limit, then you can just simply evaluate, because this would be a continuous function at that point. So I'm just going to say this is the sine, of 3 times 2 pi over 3 times 2 pi over 3. So then this is going to be sine of 2 pi over 2 pi, and we know that the sine of 2 pi is 0, so 0 over 2 pi would just be 0. Okay, kind of similarly, as theta approaches pi, nothing bad is going to happen if I plug in a pi for my theta here. I get cos squared of pi. So this will be 2. I'm just going to kind of pull out that cos squared and make it like that. So inside I get cos pi. And the cosine of pi is, I didn't need the cos anymore. Cos of pi is -1, and that is squared. So -1 squared is 1 times 2 is 2. So just actually a bit of a reminder, cross out that extra row I did by mistake. Kind of an important reminder here is that all of our work in calculus with trigonometry is going to be using radians. We're not going to use degrees at all in calculus. So we're always going to use radians, not degrees, when we're working in calculus. So sometimes we can't directly substitute in here, and we have to do some work. And these ones are going to be they may feel kind of similar to what you would have done with trig identities. So here, if we look at the limit as theta approaches 0, on the denominator here, we've got sine squared theta. We know that sine of 0 is 0. So we don't want to get a 0 in the denominator. So I'm going to do some work on this, and I might say, personally, I want to get rid of the sine squared theta on the bottom. So what I would do here is try and get like a sine squared theta on the top. And kind of looking ahead at this, if I had 1 minus cos squared, I know that that's equal to sine squared, but I just have 1 minus cos. What I'm going to want to do actually is to multiply by the conjugate here. Remember, with difference of squares, that then we would have, if I multiplied 1 plus cos theta, top and bottom, then this would be 1 minus cos squared, which in turn would be sine, and cancel out there. So I'm going to keep going. Remember that you're always keeping your limit notation through here. So we get 1 minus cos squared theta over sine squared theta times 1 plus cos theta. And then this is the limit as theta approaches 0 of sine squared theta over sine squared theta times 1 plus cos theta. And then we know we can reduce that sine squared top and bottom So we've got the limit, and now it's simplified to a point where we can sub in. And it does feel like, why do you have to show all these steps if you can kind of see what's happening? It's important to be really clear what expression you're substituting into. We cannot substitute into this row above. We can't put in a theta equals 0 because that would give a 0 on the denominator. So we have to make sure that that's reduced out and then have a simplified expression before we drop the limit. So now it's 1 over 1 plus cos 0. So 1 over 1 and cos, kept that as theta, but that should be a 0. 1 over 1 plus 1, or 1/2. Okay, kind of similar situation again. If we have the limit of 3 tan theta cos theta as theta approaches 3 pi over 2, we know that pi over 2, 3 pi over 2, 5 pi over 2, those are restrictions on tan. If you think about what the graph of the tan function looks like, they will have asymptotes at all of those values. So we can't evaluate tan of 3 pi over 2. So we're going to have to do some work on that and simplify it using very similarly to what we would have done in trig identities. So we've got 3 times sine theta over cos theta. In general, we want to get rid of whatever is not working for us, times cos theta. Reduce those out. And then this is much nicer. So we've got the limit as theta approaches 3 pi over 2 of 3 sine theta. So now this is something that's simplified and I can substitute in. So I've got 3 times the sine of 3 pi over 2. And sine of 3 pi over 2 is going to be -1. So that evaluates to -3. Notice that I keep the limit notation until I'm ready to sub in, and then I drop the limit notation out front. Couple more. Here, the limit as theta approaches pi over 2. Now, is this going to cause a problem? Cos of pi over 2 is 0, but secant of pi over 2 is actually going to be undefined because remember it's the reciprocal of cos. So I do have to simplify this a little bit first. So this will be the limit as theta approaches pi over 2, and I'm going to get rid of that secant. I'll make it 1 over cos theta times cos theta divided by 4 theta. And of course, we see that that will reduce. We do need to write it out in a simplified form that's acceptable to substitute in that pi over 2 and keep up the limit notation. You can't just sub in because that cos theta was still there. So it's 1 over 4 theta, and now we can sub into here. So we're dropping the limit notation. It's 1 over 4 times pi over 2. So it's 1 over 2 pi. Okay, similar here. The limit as theta approaches pi of cos theta, tan theta over sine theta. Now we know sine of pi is 0, so I'm seeing that I'm going to get a 0 in the denominator. So I need to do some work before we're able to substitute that in. So here I've got cos theta, tan, I'm going to make that sine theta over cos theta over sine theta. So I don't know, I'm going to write out kind of an extra step. I reduce my cos, and we've got the limit as theta approaches pi. Now we have sine theta over sine theta. So this is the limit, because that will reduce as theta approaches pi of just 1. And remember what the limit of any constant is just that constant. So that we ended up getting rid of all of our trig stuff and all of our thetas all together, and it just simplified to 1. We also are going to have some special trig limits. So we are going to take a look at what happens here as you evaluate, and this is kind of like flashback to advanced functions when we were estimating instantaneous rate of change and like estimate closer and closer. It's kind of what we're doing. What happens to this ratio, sine theta over theta, as we get really, really close to 0? So see that we're approaching 0 from both sides, and we are getting closer and closer to 1. So you see us getting like more 9s, 0.9999999. So I think that it's fair to say, and like the proof of this is really beyond the scope of what we're doing, but I think that it's reasonable to say that we see that the limit as theta approaches 0 from the left of sine theta over theta is 1. The limit as theta approaches 0 from the right of sine theta over theta is 1. So that the limit as theta approaches 0 of sine theta over theta is 1. And that's an identity that we're just going to be able to use. So the limit as theta approaches 0 of sine theta over theta equals 1. So that is just a rule, and we're just going to be able to use that in evaluating lots of different limits involving trig functions. Very similarly, the next one involves sine 3 theta over 3 theta. And the 3 is a little bit arbitrary, but you can try it with different numbers. I have filled in these values to like save some time during the video. And as you can see, it works out the same. You've got these increasing numbers getting closer and closer, but not getting bigger than 1. And you actually see quite a nice little pattern in there with how many 9s and then repeating numbers afterward. So we can say as you're approaching from the left, it's getting closer and closer to 1. As you're approaching from the right, we're getting closer and closer to 1. So overall, the limit as theta approaches 0 of sine 3 theta over 3 theta, and that 3 again is arbitrary. We're going to have that just as a constant. That would be 1. So that is another rule that we're going to be allowed to use. The limit as theta approaches 0 of sine c theta over c theta, where c is any real number that's not 0, would equal 1. I'm just going to add that. Things fall quite far apart if c would equal 0, but c can be any other real number. The last special limit is this one, 1 minus cos theta over theta. So again, we're increasing towards 0 and decreasing towards 0. And what is actually happening here? So here we see these values increasing. As we increase towards 0, the values are getting smaller and smaller and smaller negative. And here we're getting smaller and smaller positive. So we're getting closer and closer. And again, you see a neat pattern. Every time you add a 0 here, you get a little, another factor of 10 closer to 0. So we see that this is going towards 0 and this is going towards 0. So the limit as theta approaches 0 of 1 minus cos theta over theta will equal 0. So the limit as theta approaches 0 of 1 minus cos theta over theta will equal 0. And that's our third kind of special trig limit that we will be able to use that definition to solve for lots of different trig limits by rearranging to try and pull out this one or the one with sine theta over theta. And we'll do the examples in the next video.